Today we will be discussing this part of the syllabus, and with that we will also come to know some other logics behind the values of that we had given in the last class, the tables. Okay, so let us move into the class. So as we know, any an atom has 3 degrees of freedom. So a molecule having n number of molecules, n number of atoms will have thrice n degree of freedom. So therefore, what we have already seen in the last class is that what are the number of the fundamental vibrations in a molecule. So based on the number of atoms present in the molecule and the shape, whether it is linear or non-linear, we have the number of fundamental vibrations. Okay, now let's see. If it is H2O, we know it is non-linear, and then the degree of freedom, it has 3 atoms, so the degree of freedom is 3 into 3 is 9, and we have the formula that is thrice n minus 6 is the fundamental vibrations number. So it is 9 minus 6 is 3. So in the IR spectra, we expect to see 3 peaks. Supposing we take this carbon dioxide. So in carbon dioxide, we have 3 atoms. It is linear. So for linear, it is thrice n minus 5. So it is 9 minus 5 is 4. We expect to see 4 fundamental vibrations. Now let us take a different example, like formaldehyde. Now formaldehyde has got 4 atoms. It is non-linear. It is 3 into 4 is 12. 12 minus 6 is 6. So we expect to see 6 vibrations, 6 fundamental vibrations. Now what are those? What can those be? Now we know asymmetric stretching and symmetric stretching of CH2. Okay, there are CH2, there is CH2 atoms or group. So CH2 is asymmetric, will be having more wave number for asymmetric stretching, and symmetric lesser wave number. So these are coming quite closer to one another. Then we have CO stretching. Then we have CH2. These are coming in the fingerprint region. CH2 scissoring, CH2 walking, CH2 wrecking. So in total 1, 2, 3, 4, 5 and 6. Okay. Now these values we have got these values, and these values can shift depending on certain factors. So that is what we are going to discuss here. Okay, our discussion point will be effect of hydrogen bonding, conjugation, resonance and ring size on IR absorption. Like these values may shift. Now what are the factors and how it changes, how it shifts the IR absorption values. Now first of all, let us discuss effect of hydrogen. We know if a bond is vibrating or it's stretching or compressing, it has to be considered as a spring. Say for example, carbon hydrogen bond we have shown here as a spring. Now that can vibrate. Okay, it can become longer, it can become shorter. Now when it is becoming asymmetric or shorter, I mean the 2 different bonds are there, and therefore what you have to know is it can only have asymmetric stretching when you are having 2 different bonds, obviously. So any molecule will have different bonds in it. So there can be asymmetric and symmetric stretching. Now when this particular atom is such an atom which can form a hydrogen bond, okay, with a similar molecule or a different molecule like solvent. Okay, so here we have considered OH, and OH is highly electropositive, so it is capable of forming a hydrogen bond if the solvent is water. Now in that case, this H is being hydrogen and bonded to the oxygen, and therefore this bond is more in a stretched form and its bond strength decreases. So when its bond strength decreases, the absorption peak moves towards lower frequency, which I have highlighted here. Okay, and it moves to the lower frequency that you expect in a normal case. Okay, whatever frequency you are expecting, from that value it will go to the lower frequency because its bond is becoming weaker and it is becoming more stretched by the hydrogen bond formation. In further, if you think about the banding, okay, banding vibrations. Now, if you know, if two bonds are being stretched and it has been tied up with some other thing, it becomes very difficult to band it. You can take a simple your day-to-day life example. Supposing you have two flexible pencils, okay, and these pencils you have tied to some other point. Now, can you band those? Can you band the angle? You can't. So therefore, in that case, the banding frequency shifts to a greater absorption, okay, absorption value from its normal value. See, stronger the hydrogen bonding, greater is the absorption shift from the normal value. Now, in this case, it will move to a higher frequency. In this case, it will move to a lower frequency. Stretching will move to a lower frequency, whereas banding will move to a higher frequency. Okay. Now, we know already that hydrogen bonds can be of two types: intermolecular and intramolecular. Okay, intermolecular and intramolecular. Now, in case of intermolecular, what happens is that intermolecular means the hydrogen bond has been formed between two different molecules. Now, these two different molecules can be of similar type, or it can be of two different types, like the sample molecule and the solvent in which the molecule has been dissolved. Okay, so it depends on the concentration. So when it depends on the concentration, and if the concentration is higher, means more amount of molecule has been dissolved in a certain amount of solvent. Okay, that time the hydrogen bond is concentration is more, means the shift towards the lower frequency will be more. Okay, and if the concentration is less, means the number of molecules is less, and therefore the shift towards the lower frequency will be lesser. Okay, and also if it is intramolecular, suppose in the same molecule there won't be any difference in the absorption peak. It will be definitely it will be moving towards the lower frequency, but it won't depend on the concentration. So it won't depend on the concentration. So whether the solvent is present, whether the solvent is not present, whether the IR spectra has been taken in a KBR palette, means in the solid phase or in the liquid phase, it doesn't differ, means the bond doesn't differ. It will only have a shift towards the lower frequency, and also the shape of the peak will be broader. Okay, it will be round in the shape, rounded shape. Okay, it won't be having any peak, it won't be having any sharpness, it will be a rounded shape. So while considering a molecule and the solvent, we have to be very much cautious about the solvent. And the solvent, if it is such like chloroform, where the chloroform molecule is having a halogen, and that halogen has got a capacity, like halogen can interact with the hydrogen in the molecule, okay, in the sample molecule, and that hydrogen can also get shifted, and therefore the peak will be deviating more. Okay, so and next is that if the solvent, supposing we are talking about solvents such as like it has a atom in the solvent, there is an atom which has lone pair, like aldehydes, okay, or tertiary amines. So in that case also the the shift will be quite more, because this non-bonded electrons will interact with the hydrogen atom, and therefore it will be changing the shifting the absorption peak towards the lower frequency. And also we have certain types of solvent where the solvent is such that there is Cl or sulfur, but it is not having any hydrogen. During that time, what happens is that it will interact, but since most of the molecules in organic chemistry, they have lesser amount of sulfur or lesser amount of chlorine, so the interaction will be lesser. It will be a weak interaction, so therefore we can prefer to go for CCl4 CS2 as solvents. Okay, and also if the temperature is increasing, we have that if the temperature increases, it will change the degree of hydrogen bonding. So higher temperature means lesser extent of hydrogen bonding. Accordingly, it will be shifting less to lesser extent at higher temperature. So let us see some graphs, okay, or IR spectra. So we have taken the IR spectra of phenol. So here it has been taken in the vapor phase and here in the liquid phase. So in the liquid phase, you can see it is in the vapor phase it is such a sharp peak, whereas in the liquid phase it is a rounded peak. Okay, it's a rounded peak or a broad peak. So what is the reason? Reason is that here phenol is forming hydrogen bond with the other phenol molecules. Okay, it is in the liquid phase, but it is not having any solvent. So here it is in the liquid phase. Phenol is in the liquid state, and therefore the one phenol is forming a hydrogen bond with the other phenol molecule, and this hydrogen bond is making the OH bond weaker, and therefore it is having a shift in the hydrogen. See here the peak is around 3600, whereas here the peak is around 3400 or 3300. So therefore it has shifted to the lower frequency, and also the number of hydrogen OH coming together is more. So therefore it is having a broad, more amount of molecule is forming, coming into the association, and therefore it is having a broad peak. So a few more examples are discussed here. Say for example, this is actually what you see when you get a higher spectra in from a machine. This is written here, KBr disk. I think you can follow this KBr disk. KBr disk means it is having a solid phase. Okay, in the solid phase, even you can see a particular molecule is showing a broad peak. Okay, so what is the reason? And there are so different peaks are there, small peaks. So this particular peak is due to the intramolecular hydrogen bonding, because you can see solid, even though it is solid, it is not having any solvent, it is not having any liquid phase, but even then it is forming it is giving us a broad peak here. So that means what? It is a solid molecule, and in the solid molecule it is having such groups by which it can form intramolecular hydrogen bonding. Okay, so that is the meaning. Let us take this particular thing here. What you have is here it is a liquid phase in liquid film. It is a liquid film study has been done, and just like a liquid film is a very thin layer of liquid phase molecule. Okay, so it has been taken in a liquid phase. So here what you see is, it is having two ketonic group, and ketones always go for enol ketone tautomerism is always there. So this enol form OH group is there, and this OH group is capable of forming hydrogen bonding, and therefore in the liquid phase it is having lots of molecule coming together, and therefore a shift has been found from 3000 to 2900 value, 900 position. So therefore what you see is there is a big shift, and it is only because of hydrogen bond formation capacity of the enol form. And here what you see is KBr, and in KBr phase